Hello everybody, my name is Kanan Panchal and today we shall discuss surface and interfacial tension. In this video we shall discuss what are surfactants, what is HLB classification and how do you determine HLB. We shall also discuss the concepts of micelles, inverse micelles, wetting, contact angle, detergency and the applications of surfactants in pharmaceuticals. Now let us talk about surface active agents, commonly known as surfactants. Now here you can see dirt. Now say it is on the surface of a cloth or grime on the surface of a hair follicle. Water alone is not able to take off this dirt. It needs help of a soap or a surfactant molecule. Now these surfactants will arrange themselves in such a particular way and help in the removal of the dirt and thus provide a cleansing action. So at a molecular level, a surfactant looks somewhat like this. It is composed of a hydrophilic head region and a hydrophobic tail region. Now the hydrophilic head can be of four types. It can either be non-ionic, that is no charge. It can be ionic, that is it can either have a negative charge or a positive charge. It can also be amphoteric, that is it can gain a negative or a positive charge based on the pH of a media. Now pharmaceutically, surfactants are very important in many formulations and one of them is emulsions. Here you can see this is a oil and water type of emulsion. Now these surfactant molecules adsorb onto the surface of the oil and help in stabilization of these oil globules. Also here you can see they are anionic, that is having negative charge. And because of these negative charge on the surface, this creates repulsion amongst the oil globules and hence prevent the coalition of the oil globules and help in the proper stability and suspension of the oil and water emulsion. Now there exists many types of surfactants. So based on their hydrophilic lipophilic balance, Griffin in 1947 has classified these surfactants as per their HLB values. Now this is an HLB scale. It usually ranges from 0 to 18. In some textbooks you'll also find it from 0 to 20. So the above region with higher HLB values consists of the hydrophilic region or the water soluble surfactants, whereas the lower HLB values are hydrophobic and consists of oil soluble surfactants. So how will you remember this? H is for high, H is for hydrophilic, L is for low, L is for lipophilic. Now, based on the nature of the hydrophilic region, as I earlier said, they are classified as anionic, cationic, non-ionic, and amphoteric. These are some typical examples of surfactants belonging to these categories. Now, please take a note that not all of these surfactants can be used parenterally because anionic and cationic surfactants usually have a lot of irritant action. So lecithin from the amphoteric category and the polyoxyethylene polyoxypropylene type of surfactants from the non-ionic category are usually used for parenteral preparations. The others can be used for topical as well as for oral. So please take a note of this. Let us discuss some common commercial surfactants and their names. One of them is popularly known as SPANs. SPANs are nothing but sorbitan esters and they are lipophilic. Hence, their HLB values will be on the lower side. That is, it's about 1.8 to 8.6. On the other hand, we have twins, which are nothing but the polyoxyethylene derivatives of SPAN. Now, twins are hydrophilic, hence their HLB values will be on the higher side. that is about 9.6 to 16.7. Now, spans and twins are the commercial names. Let us discuss their chemical names. Span 20 is nothing but sorbitan monolaurate. Now, this is the region marked by R, which is esterified. Since there is only one esterification happening, it becomes a monoester. Hence, it is sorbitan monolaurate. Now, tween 20 becomes the polyoxyethylene derivative. So, this part of the nomenclature remains same. Only the addition will be of polyoxyethylene. So, tween 20 chemically is known as polyoxyethylene sorbitan monolaurate. Now, again here in span 60, it is sorbitan monostearate. So, similarly in tween 60, it will become polyoxyethylene sorbitan monostearate. So, if you remember, the numbers 20, 40, 60, 80 correspond to laurate, palmitate, stearate and oleate. The other names will be easier for you all to remember. Now, please note the 20, 40, 60 and 80 numbers here in spans and tweens do not indicate the number of carbon. They indicate the viscosity grade of the surfactant. Now, oleic acid, that is the span 80 and the tween 80, they are the only unsaturated surfactant in this category, since oleic acid has one unsaturation in it. To spans and tweens, we have another common surfactant called as bridge. Now, bridge is an ether. It is a polyoxyethylene alkyl ether. So, bridge 30 here is polyoxyethylene 4 lauryl ether. Now, 4 indicates the number of polyoxyethylene groups reoccurring. Bridge 35 is polyoxyethylene 23 lauryl ether. Now, how will you remember this? Now, the grades 30, that is 30, 35, they'll come as lauryl ethers. Only the number of polyoxyethylenes are changing. And bridge 56 and 58, they are nothing but cetyl ethers. Again, with difference only in the number of polyoxyethylene. Also note that spans, tweens and bridge, all three of them are non-ionic surfactants. There exist certain standard methods of determining HLB values. If your surfactant is non-ionic, having only polyoxyethylene as the hydrophilic portion, HLB is calculated by this formula, that is E by 5, where E is nothing but the percentage by weight of the ethylene oxide. And if your surfactants are fatty esters of polyhydric alcohols, the formula is going to change to HLB equals to 20 bracket 1 minus S upon A, where S is nothing but the saponification number of the ester and A is the acid number of the fatty acid. Remember that the acid number is greater than the saponification number. Now let us discuss the concept of RHLB, that is required hydrophile-lipophile balance. Now this RHLB exists for both oil and water in oil emulsions. Now RHLB is already determined empirically. So this is used for determining the minimum amount of surfactant which will be required in a mixture. Now this equation is given by Bonadio. Now here QS is nothing but the amount of surfactant in a mixture required. Rho S and rho. Here rho S indicates the density of the surfactant in a mixture. It is not the density of a single surfactant. If you have N surfactants, rho S is the summation of all the N surfactants, the total density. Now rho is the density of the dispersed phase. So if you are dealing with oil and water types of emulsion, oil becomes the dispersed phase. And if you're dealing with water in oil type of emulsions, water becomes the dispersed phase. So density of that. And Q is nothing but the percent of the dispersant. That is the continuous phase in an emulsion. So by this, you can determine the minimum amount of surfactant which will be required to stabilize that formulation. Now we all might have seen that how when you put shampoo in water and mix it vigorously, foaming occurs. Now what is this foam? This foam is nothing but air pockets which are enclosed by thin films of this surfactant liquid, right? So this forms a gas and liquid interface, right? So there are certain agents in those products which facilitate the formation of this foam and causes the stability of that foam and inhibit the coalescence of these bubbles. These agents are called as foaming agents. Now, at certain places, foaming is undesirable. That is, at industries, when you are mixing certain products, you don't want foaming to take place. So you require certain agents to break these foams. And those agents are called as anti-foaming or defoaming agents. As I said, they break these foams. And they are used for both the foam formed on the surface and the air entrapped inside the bulk. Now these agents have less viscosity and they spread rapidly over these liquid films. As they spread, the film collapses and the air bubble ruptures and this breaks open the foam. So alcohol, ether, castor oil and some surfactants which have certain HLB, they perform the anti-foaming activity. Now let us understand the concept of micellization and the story of micelles. So here in the animation you can see a dirt is on the cloth. So these surfactant molecules form an aggregate and this aggregate is called micelle. Now only after a certain concentration is achieved and crossed, that concentration is called CMC, that is critical micelle concentration, will these individual surfactants aggregate to form micelles. Now even after the CMC is exceeded, their shape changes. The spherical micelle become lamellar. Therefore the shape of micelle is concentration dependent. And the diameter of these micelles are twice the length of the surfactant. Now the individual surfactants are molecular, but when they form micelles, they become colloidal in size. Now there is something called as inverse or reverse micelle. Here you can see that the hydrophilic head is on the outside and the lipophilic tail is on the inside. When the reverse happens, that is the lipophilic tail is on the outside and hydrophilic head is on the inside, such a micelle is called inverse micelle. This usually happens in oil and water type of emulsions. So as I said, micelle formation will only occur after CMC is achieved. And above this CMC, surfactant won't have an effect on the surface or interfacial tension. Now surfactants on an water and air interface will be arranged somewhat like this. That is, the hydrophilic head will be towards the water, but the lipophilic tail will be towards the air. Now when the micelles are forming, as they are colloidal in size, a new phase is being generated, but the system will still be in a solution form. That is, precipitation won't occur. And when the CMC is low, micelle formation will readily take place. But it won't take place readily if the CMC is high. Now, on an average, to make up a micelle, about 50 to 100 surfactant molecules aggregate together. Now, this number is called as the aggregation number. An aggregation number is different for different surfactant molecules. Now, if the hydrophobic region in a surfactant is high, and if also there is presence of electrolytes in the media, the aggregation number is going to increase. And when the aggregation number increases, CMC decreases. That is, these two are inversely in proportional. Also, please note that ionic surfactants have higher CMC than non-ionic surfactants. Now, bile salts are the natural or the physiological surfactants present in the body. Even they are capable of forming micelles. So, let us understand wetting and wetting agents. Before that, let us understand the concept of contact angle once again. Now, that angle which is formed between the tangent which is drawn to the liquid drop at three phases. That is a tangent which is drawn over here. Now the three phases are the solid over which the liquid is spreading and the gas phase. Okay, and the angle is measured through the liquid. Angle can be formed here also, but the contact angle should be passing through the liquid towards the tangent. That angle is called contact angle. Now what does wetting agent do is that it tends to lower the contact angle between the surface and the liquid. That is because when the contact angle is 0, complete wetting occurs. And when the contact angle is 180, no wetting occurs. So that is, as the contact angle decreases, intensity of wetting increases and the surface tension decreases. Now this wetting also deals with adsorption. That is, when the adhesive force between the liquid and the surface over which it is spreading. So this adhesion force, when it is greater than the cohesion force between the liquid molecules, then it is able to wet the surface and hence decrease the contact angle. Now if the cohesive forces are more, wetting won't take place and the contact angle also will be relatively high. This we have seen in the capillary rise method, right? Because the adhesive force is more, the liquid inside is able to wet the surface of the capillary and hence decrease the contact angle, and thus the water or the liquid inside is rising up the capillary. Now, this is the range of the wetting or the spreading agent. It is somewhat in the middle of the HLB scale. It is about 7 to 9. So please take a note of this. Now, when you put a drop of distilled water on clean glass surface, complete wetting occurs and the contact angle formed therein will be 0 degree. But this doesn't happen in practical scenario. That is, say for example, when there is raindrops falling on your glass window, complete wetting doesn't occur. Instead, droplets like these are formed, or else trailing like this will occur. Now, angle formed by such droplets is called as the equilibrium contact angle. Now, droplets with similar circumference will have the same equilibrium contact angle. Contact angle formed by such trailing droplets on the advancing side, it is called as the advancing contact angle, and on the receding side, it forms the receding contact angle. Now, the difference between the advancing contact angle and the receding contact angle is called the contact angle hysteresis. Now, what causes this contact angle hysteresis? Either the water droplet is impure, that is having some contamination, the surface over which it is spreading is rough, or the surface is having some contamination or variability. All of this causes the contact angle hysteresis or equilibrium contact angle and doesn't allow the water to spread completely over the surface. Now we understood how wetting agents are a class of surfactants. Detergents similarly are again one class of surfactants and they are usually used for the removal of dirt. Now this is what we saw on the first slide, how the detergents or these surfactants help in removal of dirt. Let us understand its mechanism. First step is the initial wetting of the dirt and the surface which is to be cleaned. And then is the deflocculation and suspension of these dirt molecules. These are going to form micelles and help in the deflocculation. Then will be either the emulsification or solubilization of dirt particles. And the foaming agents will entrain the dirt and then wash away the particles. This is how detergency is going to take place. Now, any surfactant that is not a soap is a detergent. That is, soap and detergents are not same. Soap are fatty acid salts and usually have carboxylate group at the end. That is, they are anionic in nature. They are usually salts of sodium and potassium, and they are long hydrocarbon chain. Okay. So any surfactant not qualifying as a soap is a detergent. Now, what is going to be the effect of impurities on surface tension? If you have organic impurities, it is going to lower the surface tension. Now, that is because these organic impurities tend to go on the interface, that is the water-air interface. And the force of adhesion between these organic impurities and water is very high. Hence, it will cause lowering of surface tension. On the other hand, if you have inorganic or ionic impurities, they increase the surface tension because they are not present at the interface. They are present in the bulk, and the force of adhesion between these two is not high. That is the reason why the surface tension of groundwater or tap water is higher than surface tension of the distilled water. How are you going to remember this? I for inorganic, I for ionic, I for increase in surface tension, and the opposite, O for lower surface tension. Now, how is the understanding of surfactant going to help us with our formulation? First is selection of binders. Based on the HLB of your binder, you can select the appropriate one for your formulation. Then a selection of polymers for film coating. Say your polymer has very good wetting and spreading capability. It will form a very good film over your tablet. If it does not have, then it may cause orange peel or blistering effect, right? Topical agents. Again, how well is your product going to spread over the surface of the skin? Or what agents are you going to use to enhance that spreading? Or what agents are you going to use as permeation enhancers? All of that is required in topical products. Next is dispersed systems like your emulsions, suspensions. Emulsifiers are used in emulsions, wetting agents are used in suspensions, and they help in proper stability and manufacturing of these systems. And definitely your toiletries, your shampoos, conditioners, bathing gels, etc. So we have surfactants all around us and we use it almost on daily basis. So I hope you all understood these concepts. Thank you.